I'm Andrew Thompson, and this is my ENME435 final project. To get started, some background. We'll talk about the target of interest, the design of the LiDAR sensor, the calibration process, data collection, and finally, data processing. To get started, this is the target of interest here. It is a bench outside of the chapel here at the University of Maryland. I chose it because of its unique geometry and its location. It's in a tucked away spot that doesn't have a lot of light pollution, and there aren't many other sources of noise, so I thought this would be a good spot to get a point cloud scan. Onto the design of the sensor. It is made of several components, first of which is the mount. In the picture here, it is the white thing. The mount holds the Raspberry Pi camera, the line laser, and the Arduino. The Raspberry Pi is there to run all of the Python scripts that were used in order to collect and process the data for the scan. The Raspberry Pi camera, you can think of that as the collector. So if you think of the LiDAR sensor as emitting and collecting visible light signals, the light is provided by the line laser, so that is emitting light, whereas the camera is collecting it. The Arduino is there solely to provide power to the laser, and the tripod holds the whole apparatus and allows us to tilt it forward and backwards to scan the target at different angles. So onto the theory, I'll direct your attention to the image on the right. As you can see, the laser and the camera are located on the same plane. The data we get back is the pixels from center. So we take a picture and we count how many pixels from center the line or the laser appears. And this can be used to get an angle, and that angle due to vertical angles is the same as the angle shown marked by theta on the diagram. So this angle is also described by trigonometry. This distance h is a known value. It's the distance between the laser and the camera, so we design that to be 1 foot. And this creates a relationship where d is proportional to 1 over tan theta. So adjusting the angle at which we point the whole apparatus, we can create that relationship with the distance. Onto the testing and calibration. So in order to calibrate this setup, I took the tripod and placed it in front of a blank wall and took pictures of the laser on the wall every 6 inches. So take a picture, move it back 6 inches, input the distance, take a picture, move it back, input the distance, take a picture, and then move it back again. The results are displayed on the right. So on the x-axis, we have that pixels from center, where the line is, and on the y-axis, we have the distance to the target. Um, as you can see, the experimental data matches up pretty well with the theory, marked in blue, and this curve follows that 1 over tan theta relationship as discussed in the last slide. Finally, I'll play some video that was collected during my data collection. All right, how's it going? I'm here outside the chapel taking my scans for the 3D point cloud. So here is my process here. I have my data collection file, and when I run that, it'll ask me for IMU data. The phone I'm using to film, I set up in line with this holder and make sure that I get the angle reading, and then I'll put that in here and click enter, and then it'll take a picture of the laser line on the subject. I can turn this nozzle and loosen the apparatus, and then I can tilt it forward or backwards, and I'll get a new angle and be able to move on to the next image. So as you can see here, I plan on taking scans on the left, in the front, and on the right. There is limited space here on the left and the right, so I'm not sure how those scans will come out. And then there's almost no room in the back, so probably won't be able to scan the back side either. But I'm hoping to get a good scan of the sides and the front here, and we'll see how it goes. All right, how's it? So now on to the results. Hello everyone, I'm here to show you my finished point cloud. So for reference, the object that I made a 3D point cloud of was this care bench. And the first thing I did was took the data and then used data generation.py to process the data. I took the points generated from this data generation script in here, and I did that for all 5 of my scans. The main tools that I used were apply transformation and crop. So there was a lot of noise, so I got rid of all the points that were not as important, and I'll show you. When you do apply transformation, you get the opportunity to use either the top 3 by 3 matrix for rotations, or this column here for translations. So by manipulating this homogeneous transform, I was able to create this point cloud. As you can see, some letters generated better than others. We've got the C here and the A, they look pretty good. And then the sides of the C and the E. I could not get behind this object just because there were, I don't know if you noticed in the picture, but bushes right up behind the bench. But all things considered, I'm happy with how this turned out.